My dear friends, welcome back. This is Ratnam from Government Degree College, BODHAN. Today, my lesson is Structural Theory in Organic Chemistry. This is part of first year, BSc, first semester, organic part. And this is an introduction of organic chemistry for BSc courses. We know that organic chemistry is developed based on the nature of the carbon and the speciality in making different combinations of carbon with the hydrogen and with heteroatoms like oxygen, nitrogen, and halides, and so many other atoms. So this nature of carbon, the tendency of the carbon to form different types of bonds with other atoms, and also self combination, that is carbon contains its own combination with carbon carbon bonds, and there are so many several type of bonds like C single bonds, C double bond C double bond C, and also CO C double bond O, C N C double bond N, C triple bond N. So like that, several different sorts of combinations are possible. All that put together is called organic chemistry. And now let us take up some of the features and important points as given in the syllabus of first year organic part. So this is structural theory in organic chemistry. Look at now. Let us try to understand the nature of covalent bond. First of all, we should know that a bond is nothing but whenever two atoms combine with two electrons, that is called a bond. A bond means it is two electron combination. So two electrons represent a bond between two atoms. Depending on the position of these two electrons, we generally divide this bonds into different types. For example, if two electrons are shared equally by the two atoms, then it is like covalent in nature. We call such bond as covalent bond when two electrons are shared by two atoms equally. That means the electron clouds are in between two atoms. If the two electrons are attracted or move towards a single atom, then that gives a negative charge to a particular atom, and automatically the other atom gets positive charge. So such type of bond formation is there, having ions. Then it becomes ionic in nature. That is called ionic bond. Similarly, we have based on the nature of the electrons shared by the atoms. For example, if the only one atom is providing two electrons, then that is called coordination bond. Of course, it is coordination covalent bond, but the nature of donation of two electrons by single atom. Here, at this level, we are discussing covalent bond of organic molecules. It is a bond formed by equal sharing of electrons. Carbon, for example, if you look at the valency of carbon, carbon is the fourth group element, and the valency electrons are 4. But what happens with carbon? Can it gain extra 4 electrons to become a noble gas configuration, stable configuration? No, it cannot gain electrons 4 altogether. Similarly, it cannot give total 4 electrons to others. That means it cannot form any kind of ionic bond, because to form any ionic bond, either it should lose electrons or it should gain electrons to become C minus or C plus. So in neither case it is not suitable either to lose electrons or to gain electrons. That's why carbon cannot gain 4 electrons or cannot lose 4 electrons. Therefore, it prefers to share electrons. That's it. So sharing of electrons is more convenient for carbon because of its valency number 4. That is the main reason why it forms covalent type of bonds. That's why most of the cases carbon forms covalent type of bonds, and all the organic molecules we whatever we discuss, They are all having covalent bonds. So this is what we call as to get the noble gas configuration. Carbon is ready to share electrons, and since the valence is 4, every carbon must have 4 bonds, must be covalent bonds. What is this bond polarization? How do we understand this? For example, just look at this. Yes, this bond polarization. Here, you can just see the examples on the left side. Two atoms are there. Let us take them as the same atoms. For example, H2, hydrogen, hydrogen. Both are hydrogen atoms. Since both are same, so their electronegativity will be same. Electronegativity is nothing but the ability of attracting electron pair is called electronegativity. So here, if you take hydrogen, hydrogen, since both are same atoms, so the electronegativity of hydrogen, hydrogen is equal. Therefore, they equally attract electron pairs. So when a bond is formed between two hydrogens which are similar, then the bond electrons, that is bond pair of electrons, are equally attracted by both hydrogens. Therefore, the electron pair is exactly in between the two atoms. As you can see on the left side diagram, they are equally shared. So when such sharing is possible, then it is called a perfect covalent bond. And here we are using another word, non-polar covalent bond. What we mean by non-polar covalent bond means it is not having any kind of polarity. What is polarity here? Polarity means any deviation or any distraction in the electron cloud. If electron cloud is slightly towards any atom, slightly more towards any atom, then that atom gets a slight partial negative charge. Automatically the other atom gets a slight positive charge. So this kind of what charge separation, positive negative charge separation, it may be very small, partial, or it may be full, but whatever the charge separation, if it is possible, then that is called polarity. Polarity means plus minus separation. So in non-polar means the electron cloud is equally distributed between two atoms. Therefore, there is no what there is no change in the electron cloud density on both atoms. Both are having same. That's why there is no polarity. There is no positive or negative charge on any of the two hydrogen atoms. Such bond is called non-polar covalent bond. Just look at the other atom. For example, CH. Let us take one example, CH. In the second one, in the middle one, the CH means the electron cloud is more towards carbon when compared to hydrogen. The hydrogen is slightly getting positive charge because the electron cloud is more towards carbon. Therefore, carbon gets slight negative charge. So, such a combination where one atom is getting more electron cloud and therefore negative charge, partial negative charge. The other atom less electron cloud, therefore a partial positive charge. So this kind of positive negative charges are developed into atoms. Therefore, it is called polarity is developed. Since the bond is having polarity character, therefore that kind of bond is called polar covalent bond. This is second type of bond. And if you extend the same concept, that is the electron cloud is more towards one atom, then suppose the two electrons are completely taken away by the one atom, and the second atom is not having electrons at all. Therefore, the second atom becomes positively charged because it has lost its electron, and the negative charge is accumulated on the other atom where the two electrons are totally shifted. Now, what happened? To the right side, you can see two ions are formed. That is, the electron cloud is completely shifted to one atom which is getting negative charge, a complete negative charge, and the remaining atom is getting complete positive charge. So such combination is called ionic type of combination. It is also bond, but it is exhibiting ionic nature. Therefore, this is called ionic bond. A completely polarized bond. You can call it as completely polarized bond. So now you just compare these three bonds. These three bonds are called non-polar covalent bond, polar covalent bond, and ionic bond. And purely this is due to the nature of two atoms. When you take same type of atoms like hydrogen hydrogen, it gives non-polar covalent bond. If you take two atoms with different electronegativity, whenever you take two atoms with different electronegativity, if the electronegativity difference is very small, then it gives polar type covalent bond where electrons are slightly shifted towards more electronegativity atom. And if you take two different atoms with what large difference in electronegativity, for example HCl, then HCl, in that particular HCl, H is getting total positive charge because it loses its electron, and chloride being a more electronegative nature, it totally gets the electrons towards it, and chloride becomes Cl minus ion and H becomes H plus ion. Therefore, that is called ionic bond. You see here, this is polar and non-polar bonds. If you see two carbons on the upper side, both are carbons. Therefore, the electron cloud is equally distributed among these two carbons. Therefore, it is perfectly called a non-polar covalent bond, as we were discussing just now. The bottom side, you see oxygen, hydrogen. Now, when you compare oxygen, hydrogen, the electronegativities are different because both are different atoms. Then naturally, the more electronegative atom attracts electrons. Here, the more electronegative atom is oxygen, so it attracts electrons towards it, and hydrogen becomes less uh, uh, electronegative in here nature. So the electron cloud is very less at hydrogen, and it is more at oxygen. What happens? Partial negative charge on oxygen, partial positive charge on the hydrogen. Therefore, it is a polar. Now the concept has become polar. Therefore, it is called polar covalent bond. Now let us get back to our bond polarization here. So this type of nature, because of the difference between the electronegativity of two atoms, because of the difference in electronegativity of two atoms, there we can expect polarization. If electronegativity is not difference, then polarization is not there. If electronegativity difference is becoming more and more, polarization becomes more and more. This is what we call as bond polarization. That is, shifting of the bond electrons towards one atom is called bond polarization in simple words. Fine. Now look at this H2O molecule. It is pure polar molecule. We can call water as polar solvent also. The reason here, you can see oxygen being more electronegative when compared to hydrogen. It is attracting two electron bonds. That is, there are two OH bonds, and both the electron bonds, that is, the bond pairs, are attracted towards oxygen. Therefore, it gets a partial negative charge. Simultaneously, both the hydrogens are losing the electron cloud, therefore they get partial positive charge. So overall, there is a dipole, that is, there is a polarity in the molecule itself, and this is what we call as bond polarization. And whenever such bond polarization is possible, then we expect a permanent dipole nature in some molecules. It is depending on the structure as well as the atoms involved in the bond polarization. So here is a good example of water molecule where we can expect a permanent dipole nature as shown in the diagram. So this is what we mean by. So already we have been discussing the point that bond polarization is mainly due to one factor, exclusively one factor, that is electronegativity. Of course, there are so many other factors, but the most important factor is electronegativity. Already I told you that electronegativity is the tendency of any atom to accept the electron pair or to attract electron pairs is called the electronegativity character. So whenever there is a difference in the electronegativity between the two atoms which are sharing the electron pair, then bond polarization takes place. If there is no difference in the electronegativity, no bond but polarization takes place. So this is the fundamentally very important concept to understand the organic chemistry, because bond polarization is the key and the most important point due to which several mechanisms, several there are several issues which we generally come across in the lesson, where we can understand very clearly if we understand what is bond polarization. Okay. So already there is a order of electronegativity order. Fluorine is highest electronegative, that is its electronegativity value is very high. Then comes oxygen, then comes chlorine, then comes nitrogen, then bromine and iodine, and so on. Hydrogen, carbon is 2.5 and hydrogen is 2.1. So hydrogen is the least. Then after hydrogen it is metal. Metals are generally electropositive in nature. Generally they don't have electronegativity character. Because electropositive means they lose electrons. Instead of gaining electrons, they lose electrons. That's why metals behave like electropositive in character. Now, let us go back to our input. Already we have seen this bond polarization. And due to bond polarization, we are now getting into the main part of our lesson. That is, what are the impact for bond polarization and what different effects we can expect through bond polarization. One is inductive effect, and second is mesomeric effect, and third is hyperconjugation. So these are the three effects which we are going to discuss in this lesson. What is inductive effect, what is mesomeric effect, and what is hyperconjugation. Let us understand them one by one, and let us take up examples and applications of these three effects to understand the organic molecules. What is inductive effect? Let us try to understand this. Inductive effect is it is actually in sigma bond. Inductive effect comes in sigma bond. Here it is a permanent effect. It is due to perfectly due to the difference in electronegativity, a permanent displacement of electrons forming a covalent bond towards the more electronegative element of RNA group is called inductive effect. That is due to the difference in the electronegativity of two atoms, the electrons, sigma electrons, specifically sigma electrons, move towards or they shift towards a more electronegative atom, partially, not completely. Here we don't expect any ions, but it is a partial shifting or movement of sigma electrons as shown in the diagram you see here, because on the right side we are having chlorine atom, and we know that when compared to carbon, the chlorine is having higher electronegativity. Already we have seen that order of electronegativity. Here chlorine, because of its high electronegativity, this sigma electrons between carbon and chlorine, chlorine attracts that sigma electrons towards it. Then chlorine gets partial negative charge. Automatically carbon gets partial positive charge. And again, what happens? So the first impact is on the first carbon. The effect of chlorine is very high in the on carbon number one, that is which is near to the chlorine, and this effect continues to the second carbon, and it continues to the third, also continues up to fourth carbon. But it is almost negligible when you take fifth part. So it is almost negligible in the fourth part, but it becomes almost zero in fifth. Why? Because the effect of chlorine is there on the carbon. Due to chlorine, carbon is getting partial positive charge plus delta. And due to this partial positive charge, this carbon attracts electron pairs between carbon and the second carbon. That is C1, C2. and that C1 C2 bond is slightly shifted towards C1, that is towards right side. And due to this the second carbon, that is C2, gets delta delta plus, that means still partial positive charge, which is less than C1. This more delta means very very less, the partial positive charge is less. And due to the second carbon positive charge, again it attracts electron pair between C2 and C3, and this effect is continued on to C3, that C3 gets 3 delta positive, which is very very less. So more number of deltas means less positive charge. That is what we have to understand. It is not the vice versa. Don't think that more positive charge means more delta. No, no, more delta means less positive charge. So the inductive effect is very strong on first carbon, and it becomes weak when it goes to second, and still it becomes weak when it goes to third, and still it becomes totally weak, almost negligible when it goes to fourth or fifth. So to the maximum extent, we can extend this up to um, third element. That means after 3 bonds, we can expect this. But after that, it is not possible to expect any inductive effect. So it is purely uh, based on the sigma electron shifting and due to difference in electronegativity. And here sigma electrons are involved, and the shifting movement is shown with arrow mark. So the symbol arrow is uh, given towards more electro elements. Okay. Um, Already we have seen, we explained this. It is due to electronegativity difference, and it is only possible in sigma electrons. And this magnitude is inductive effect decreases while moving away from the group which is causing this effect. And if you go away, then the inductive effect will be very very less. The first carbon will be having more impact, and it is a permanent effect. So it is not temporary, it is a permanent effect. And definitely due to this inductive effect, there are so many things which we can understand the physical and chemical properties of a compound. Now let us try to understand what are different inductive effect. Inductive effect is positive and negative. There are two types of inductive effect. Means simply we can understand what is the meaning of positive and negative, because already we told that it is the movement of sigma electrons or partial shifting of sigma electrons towards more electronegative atom. So if the electrons are attracted towards the group, okay, the electron withdrawing nature of the groups or atoms is called negative inductive effect. It is indicated with minus I. That means whenever any group is attracting electron pair towards it, or whenever a group is behaving more electronegative in nature, then that is called minus I effect. That means whenever organic molecules we take, everywhere we find carbon. So any atom which is more electronegative when compared to carbon, all such groups are called as negative inductive affecting groups or minus I groups. So you can see here, we can see here, for example, NO to nitrogen. So nitrogens are more electronegative, therefore they exhibit strong minus I effect. They attract electron pair, sigma electrons very strongly towards them. Cyanide being due to the nature of nitrogen again. Then if you take sulfonic acid, sulfur also being, so it also attracts electron pair. CHO, CO, COH, COCl, CONH2. Just leave that, because whenever there are heteroatoms, they attract electron groups oxygen, nitrogen, oxygen, and fluorine, chlorine, bromine, iodine. All these attract electrons towards them. That's why whenever they are connected to oxygen, carbon, then that sigma electrons are attracted by the group which is called minus I effect. That means simply you try to understand that minus I effect is any group which attracts electron pair towards it. Similarly, the opposite, we have plus I effect. more or less we have only less number of examples for positive inductive effect. Here electron pair is given away. That means the group which what electron releasing groups, they are called electron releasing groups, are they push the electron sigma electrons towards other group. That means they push from themselves to the other end. So that effect is called plus I effect. That means they do not attract, instead they push the electron pair to other, towards other atom. Good examples here are, we can, this effect is more very strong plus I is alkyl groups. All alkyl, or we can use R or alkyl groups here. So alkyl groups here we see here, this is alkyl group, this is tertiary carbon. So that means tertiary carbon, because of three methyl groups on here, this is exhibiting very strong plus I, and this is secondary, still plus I. This is primary with less plus I effect, and methyl is very less, and hydrogen is almost lowest. So depending on the nature of the branch, so tertiary carbon and secondary carbon, primary carbon. So tertiary is highest plus I effect, secondary is next, primary is next, and methyl is very less plus I effect, showing groups. Here the interesting point also is that why generally methyl groups exhibit this positive inductive effect. Because anyhow this is carbon attached to another carbon. Okay, the methyl group is here, is now as a group, we are considering methyl as a group. So it is connected to organic molecule, means another outside also there is one carbon. So then carbon carbon means should not be any kind of effect there, but still methyl groups exhibit this kind of nature. Why this is? The reason is because of the difference in the electronegativity of carbon and hydrogen. Carbon is gaining electrons from hydrogen. Hydrogens are less electronegative when compared to carbon. Carbon value is 2.5, hydrogen value is 2.1 electronegativity value. Because of that reason, carbon is partially getting negative charge when compared to hydrogen. So due to this partial negative charge on carbon in a methyl group, what happens? It releases, or it pushes the electron pair towards other group. So overall methyl group pushes electron pair towards other group. The reason for this is that these three hydrogens being less electronegative, they what push electrons towards carbon. Naturally this carbon push electrons to other group. Therefore methyl groups or any alkyl group behave like a positive inducting effect. They exhibit that. Now let us take up the applications of inductive effect. There are very, very important applications. One of the most important is the stability of carbocations. First of all, you have to understand what is carbocation. Carbocations are nothing but any carbon with positive charge is called carbocation. This is also called as carbonium ion. So here you can see carbon with positive charge. Now, stability. When we question or when we discuss about the stability of anything, carbocation stability means the charge, that is the positive charge on the carbon, should be less. If the positive charge is minimized, it becomes more stable. If the positive charge is increasing, then it becomes less stable. So it is simple to understand. So whenever we talk about any ion, the ion is more stable if and only if the charge is less. If the charge is more, it is less stable. If the charge is less, it is more stable. So stability of carbocations means whatever, if the groups which are present on the carbonium ion, if they could reduce the positive charge, then naturally that becomes more stable. If they increase the positive charge, then it becomes less stable. So this is the main point what we have to understand here. So positive charge, how to reduce positive charge? If you want to reduce positive charge, then we need to uh, what supply electron cloud, or we need to shift electron cloud towards positive charge. Then it becomes less. That is the carbonium ion effect is reduced. So whenever there are groups attached to carbonium ion, if it is the groups which are attached to carbonium ion, if they push electrons towards carbonium ion, then such cases the positive charge is reduced, therefore stability increases. Here, so what we have to understand is, if the carbonium ion is having plus I affecting groups, if carbonium ion is having plus inductive affecting groups, plus I affecting groups, what they do, they push electrons towards C plus. Therefore what happens, C plus ionic charge decreases, and automatically stability increases. So here you see, this is the tertiary carbonium ion, and this is secondary carbonium ion, this is primary, this is methyl. So naturally, in the center, carbon is having positive charge on each molecule. Here, when you take methyl, there are three hydrogens which actually they also push electrons. The sigma electrons are given, but less. Here, there is no plus A effect in methyl. Whereas if you take primary, there is one methyl group as substituent, and already we know that methyl groups exhibit plus A effect. So how many groups are exhibiting plus I? Only one group. If you take secondary as example, here there are two methyls. You see, there are two methyls. So the two methyls means there are two groups which are showing plus I effect. Therefore, what happens? Due to these two plus I effects, the positive charge is still reduced. Now look at the third one. Here there are three methyl groups which are exhibiting plus I effect. Therefore, what happens? Due to the impact of three plus I effects, the positive charge is still reduced. Therefore, tertiary, due to plus I, three plus I groups are there, it is more stable. In secondary, there are only two plus I groups, therefore less stable. In primary, there is only one plus I group, methyl, so still less stable. And methyl is least stable when compared to this series. So carbonium ion stability is explained based on plus I effect in such a way that if it has having substituents, there are three substituents, tertiary is more stable, two substituents in secondary, so little bit less, and primary has only one plus I substituent. When compared to methyl, the stability order is tertiary, secondary, primary, and methyl. Of course, the same explanation is given to carbanions. Here in carbanions also, it is reverse order. Why? Because methyl groups exhibit the same effect. But carbanion is nothing but the carbon having negative charge. In the previous example, we are having carbonium ion. That is, carbon is having positive charge. So their electron releasing groups are useful. Stability increased. Here electron releasing groups are present. Then what happens? Negative charge further increases, isn't it? So if negative charges increase further, stability decreases. Therefore, the order is quite reverse. Here the methyl carbanion is more stable because there is no plus I effect here. Therefore, high stability. And in primary, 1 plus I effect, so stability decreases. In secondary, 2 plus I effect, stability further decreases. If it is having 3 plus I groups, the stability is least. So tertiary is least stable. When we compare carbanion, now the most important thing what we have to understand is the acidic strength of carboxylic acids and of course phenols. This can be explained by using inductive effect very clearly. First of all, let us try to understand what is the acidic strength of carboxylic acids. Carboxylic acid is any group having COOH, COOH, where C double bond O and OH. So acid means any if COH group loses proton, H plus is given away, then that is called acidic nature. So why it loses electron? Why it loses proton means once it loses proton, then COO minus, this is carboxylate ion is formed, which is more stable. So whenever carboxylate ion is more stable, then it behaves as a strong acid because it can easily give proton to others. So this easiness of donating proton is called acidic nature. So when we compare the acidic strength. We have to compare the stability of carboxylate ion. If carboxylate ion is more stable, then it is behaving as a strong acid. So strong carboxylate ion means strong acid. Again here COO minus is the carboxylate ion. Since it is having minus charge, it becomes more stable if the charge is reduced. Same principle. Whenever we are talking about any ion, the point here that the charge should be reduced. So we know that which can reduce the electron charge on COO minus? Electron withdrawing groups. That is minus I affecting. If there is minus I affecting groups attached to COOH, then they can attract sigma electrons towards it. When, as you can see on the left side, electron withdrawing groups. So any electron withdrawing group can attract electron pair back towards the group. So naturally the negative charge is reduced on COO minus. Therefore it becomes more stable. Therefore it is a strong acid. So acidic character is increasing. But if you have on the other side plus I affecting groups attached to COOH, then what happens? They push electrons, and due to this the negative charge increases. So when negative charge is increasing, the acidic character is decreasing because it is becoming unstable. So when the negative charge is more, it won't leave proton. Proton is not easy to go away. That is the reason why electron releasing or electron donating, that is plus I groups reduce acidity, minus I groups increase acidity. So this is the point what you have to understand. Now let us get back. Whenever such explanation is there, then let us take a good example here. Two examples: formic acid and acetic acid. Look at here. COOH is there, formic acid, to which proton is one proton is the substituent. So what is the nature of proton? Is it a plus I group or minus I? It is nothing. It is neither it is a plus I nor minus I. Now look at this. It is acetic acid. Acetic acid, the substituent is methyl group. So the only difference here between formic and acetic acid is here it is having hydrogen, here it is having methyl as substituent. Methyl group is exhibiting plus effect. We know. Due to the plus effect, what happens? Electrons are pushed towards COOH. Therefore, the acidic character decreases because proton cannot go away. When there is no methyl group, so plus I effect is not there. Therefore, what happens? This proton can be removed little bit easy when compared to acetic acid. So when you compare the acidity of acetic acid and formic acid, then definitely we say that formic acid is strong acid than acetic acid. The reason is in acetic acid we have plus I methyl group substituent, whereas in formic acid there is no plus I group. Okay, if you take propanoic acid, that is CS3CH2COOH, then it is exhibiting more plus I group, more strong plus I effect, due to which it becomes less acidic in nature. So if you take propanoic acid, its acidic character is still less than acetic acid. So this is how we have to compare. So with the increasing plus I groups, the acidity decreases. If you increasing minus I groups, acidity increases. You take one other example here. See this group here, the acid strength. This is pure acetic acid, and this is having one fluorine substituent here, monofluoroacetic acid, or we can call as alpha because it is in the alpha carbon. This fluorine is attached to, that is monofluoroacetic acid. This is difluoroacetic acid. This is trifluoroacetic acid. Then what happens? So in everywhere everything is same. All are acetic acids only. But here it is only acetic acid. But here it is having one fluorine. Fluorine is exhibiting very strong minus I effect. So very strong minus I effect group is one. Fluorine is present. Therefore the acidity increases. And if you take difluoroacetic acid, there are two fluorine atoms which are exhibiting minus I effect. Therefore acidity further increases. And there are in trifluoroacetic acid, since we have three fluorine atoms attached to acetic acid, due to the minus I effect of three fluorine atoms, they very strongly attract sigma electrons of COOH group. Therefore, the negative charge is further reduced, hence acidity increases. So on the same carbon, with increasing number of fluorine atoms, acidity increasing. So when you compare acetic acid, fluoroacetic acid is more acidic, difluoroacetic acid is still more acidic, and trifluoroacetic acid is stronger acid when compared to other groups. So this is what we have to understand. Here, look at the question again. Here we are having same acetic acid, but with the chlorine atoms, substituents. So pure acetic acid, monochloroacetic acid, dichloroacetic acid, trichloroacetic acid. Naturally, what we expect? Definitely, trichloroacetic acid is the strongest acid when compared to dichloro, and monochloro is still weak acid when compared to and dichloro, and pure acetic acid is weakest acid here. So pKa value is what the value which measures acidic character. Lesser pKa means strong acid. What you have to understand is Ka should be higher, pKa is lower. If you measure with Ka, then the Ka value should be higher to become strong acid. Here you see the third example, and this is a little bit interesting. The third example. Here we are having chlorine atom. This is 1, 2, 3, 4. So butanoic acid. In butanoic acid, in the third example, butanoic acid we are taking. The chlorine atom is on the third carbon. That is, this is alpha, this is beta, this is gamma. This is gamma position. The chlorine atom is gamma. Here the chlorine atom is present in the beta carbon. Here the chlorine atom is present in the alpha carbon. So the position of minus I group, is also very very important. If the position is near to the carboxylic acid, then it exhibits a very strong effect. So the minus I effect is very powerful when it is in alpha position. Therefore, alpha chlorobutanoic acid is stronger because the position is alpha. And when it is in the beta position, the impact is very less. This is the effect of chlorine atom is less. Therefore, it becomes less base, less acidic in nature when compared to alpha. And if you take gamma chlorobutanoic acid, the effect of chlorine minus I effect is very very less. Therefore, it is still weak acid. So again, you compare this acidity. Alpha chloro is strong, beta chloro is less, and gamma chloro is least acidic in nature. So all are same type, but the position of chlorine atom is different in positions. Yeah, you can see here same here acetic acid again, and one time we are substituting with some different heteroatoms. Here it is substituted with iodine, that is iodoacetic acid, again bromoacetic acid, chloroacetic acid, fluoroacetic acid. Simply you can compare the electronegativity effect of fluorine is highest, therefore fluoroacetic acid is very strong acid, then chlorine, therefore chloroacetic acid next, then bromine, it is again the acidity is less, iodine having minus effect very less, therefore the effect of iodine is very less, it is still weak acid, and pure acetic acid is anyhow no heteroatom, therefore it is least acidic in nature. So this is what we can understand. The position is also important, and the heteroatom, which is that heteroatom, is also important. So these are the factors which are important to understand when we explain the stability of carboxylic acids and the strength of the carboxylic acids. Yeah. One more important feature of inductive effect is the basic character of amines. Again, we have to understand what is the meaning of the basic character of amines. How do we understand basic nature of amines? Um, yeah, basic nature of amines is explained as the ability or the tendency of giving electron pair is called basic strength or basic character. So the stronger tendency of donating electron pair is strong base. If it has a less tendency to give electron pair, it is weak base. So depending on the ability of donating electron pair is we calculate the basic strength. So here also you look at this good example: ammonia, pure ammonium, and methylamine and phenylamine, that is aniline. So here, when we compare the plus inductive and minus inductive effect, when compared to methyl, when compared to pure ammonia, whenever there is a methyl group substituted amine, then methyl is having plus I effect. Due to plus I effect, what happens? Electron pair is pushed away, therefore it can easily donate electrons. So whenever plus I groups are present, it becomes easy for ammonia to donate electrons. Nitrogen can easily donate electrons. Therefore, basic strength increases with plus I groups, and basic strength decreases with minus I substituents. Therefore, alkyl amines are stronger bases when compared to pure amine. Okay, you look at this place. And primary is having only one alkyl group, and secondary is having two alkyl groups. So 2 plus I, and tertiary is having 3 plus I. Therefore, it must be very strong, basic in nature. But when you take the practically, when you observe, secondary is strong when compared to tertiary. Tertiary is having less basic character. Even sometimes it is less than what primary. The reasons is nothing but steric factors are important when basic character is observed. Because of the bulky nature of methyls and ethyls in tertiary, the nitrogen cannot give electrons because the receiving group cannot come near to nitrogen. This is called steric hindrance. So due to steric hindrance, tertiary amines are less basic when compared to secondary. So it is the secondary which is highest, very strong basis. Then comes primary in some cases, or tertiary in some cases. For example, if you take ethyls, it is the what secondary, tertiary, and primary. That is the order. If you take methyls, then the order is secondary, primary, and tertiary. The reasons are a little bit different. So this is up to now we had a discussion of the basic character of amines with respect to inductive effect. So with the plus I groups, the basic nature increases, and if you have minus I groups on same amine, then the basic character decreases. So this is all about inductive effect, positive inductive effect, negative inductive effect, and how this inductive effect explains the carbonium ion stability order, number one, carboxylic acid acid strength, number two, and basic character of amines, number three. So these are the three important applications which we have to understand by using inductive effect. And in the next session, we will continue this effect, mesomeric effect and hyperconjugation. Thank you very much for watching this video.